there's a 5 kilogram crate sliding down a smooth ramp. What does that smooth mean? No friction. It's elevated at an angle of 38 degrees. The length of the ramp is 2 meters. What will be the speed of the crate at the bottom of the ramp? So we know how to do this using kinematics, but the question is, how do we do this using work energy? So here's 38, and here's our crate. What are the forces working on our crate? We have gravity, and what's the other one? Our normal. Okay. Once we have our gravitational force, what should we probably do on our diagram? Draw our components. Good. What is the component down the incline? Incline is sine. And then the component of our weight force opposite the normal force is cosine. All right, so we know mass is 5 kilograms. We know the displacement down the incline is 2 meters. And what would our initial velocity be? 0 meters per second. And then we let go. It starts sliding for 2 meters, and what are we looking for? That final velocity. Okay, so listen, I'm letting you guys know we're going to use this with the work energy, but some of the giveaways are when we're talking about velocity, right? That should be one of the giveaways that we can even use that, all right? Because if you have an object with velocity, we know it's accelerating, we know it has kinematics, but now from this unit, we know that there's some sort of kinetic energy then. All right, anytime we have velocity, you have kinetic energy. So a change in velocity means there's kinetic energy. So let's go to our net work equals the change in kinetic energy. And what do we know about our net work? What's another equation for that? So now I have an equation for net work, but I know we also can set that equal to our change in kinetic energy, 1/2 mv squared minus 1/2 mv naught squared. Okay, so here's the thing. We've done problems where we've only done part of it, right? So if we look at the example before, we first set this up and we're like, oh, you know what? Like, we're going to find work, and it's only going to be equal to that change in kinetic energy. Over here, we're like, all right, now work is also equal to the force times the displacement times cosine. But the thing is, work is work. Set them equal to each other. Okay, so here's your other option. Yep. And we know our initial velocity is 0. Perfect. We are trying to solve for this velocity right here. What cancels? Oh, nothing cancels out yet. Let's keep going. Let's take a look at our diagram. And what is the net force on our diagram? It will be, but what is it like by looking at the diagram? So not numbers. Yeah, mg sine theta is our net force. Is everybody good? So this is the force causing the block to actually slide down this smooth ramp. All right, times d. So tell me this then. How does the direction of the net force compare to the direction the object's being displaced? It's the same. So what happens to cosine of theta? It's 1. So cosine of theta equals 1 since the net force and the displacement are in the same direction. The minute you know they're in the same direction, your equation is really just net force times displacement. So cosine equals 1. So then this equals 1/2 mv squared. Now we're trying to get v squared by itself, so what happens with the m's? They cancel out. And I can multiply both sides by 2. And then I can take the square root of both sides. So then we get the square root of 2 times 10 meters per second squared times the sine of 38 times the displacement, which is 2 meters. And when you plug all that in, what do you get for velocity? 4.9. Yeah, 4.96 meters per second. It does just ask for the speed, so we're not going to worry about the direction. So this is the speed of the object down the ramp.